Hello class, and thank you for watching. In this third and final part of section 3.2, domain and range, we're going to go over how to find the domain of a function or a relation using ordered pairs and the actual equation rule of the function. We'll begin by looking at the domain of a set of ordered pairs. Now, as a set of ordered pairs, the domain is simply going to be the set of first components, and the range is the set of second components. So in the first example that we have right here, our domain is simply going to be the set of the first component. So 2, 3, 4, 5, and 6. While the range is the set of second components. So the number 10, 20, 30, and 40. You'll notice that I only wrote the number 10 once, since it appears twice in our list there, and you only need to write it once. So for the second example, here's our function written as a set of ordered pairs, and the domain is the list of first components: -5, 0, +5, 10, and 15. While your range is simply going to be the list of second components. So 4, 0, -4, -8, and -12. Now your list does not have to be in any order, from greatest to least, least to greatest. As long as you have your list there and you account for every number, with the exception of repetition, you don't have to write numbers that are repeating, like in the first example, more than once. Now, if a function f is not modeled or is not modeled by data or a verbal condition, its domain is going to be the largest set of real numbers in which the function is going to be a real number, so where the output is going to exist. In most cases, the domain of the ones that you studied in Algebra 1, your your linear function, your line, your quadratic function, and your exponential function, those have domains of all real numbers. Like in the example right here that we have here, that f of x is equal to x squared minus 1, that's going to be a quadratic function. Let me draw a sketch of this. That has been shifted 1 unit downward, and like this. So the domain of such a function is going to be all real numbers. There is no restriction on this function. And the same thing with this function down here. This is again a cubic function, a polynomial function, and the domain for such a function again is all real numbers. Now, there are two functions that we're going to be studying today that do have restrictions on the domain. The first one is the reciprocal function, which aka the rational function, and the second one is the square root function. So let's review those. Now, the two functions that we're going to study today that have restrictions on the domain are the reciprocal function, whether it's the reciprocal that we have here, or the reciprocal squared function, and the square root function. These functions have restrictions on what numbers are allowed to be used for the input value of x. For the first two, for these that have no transformation, the restriction is that the denominator, again x, cannot equal to 0. So we have to restrict the situation where we cannot divide by 0. And the square root function has a restriction that because we're taking square roots, this input value, again the radicand, has to be a number that results in a positive output value. Because if I plug in a number and the output value is negative, I will not be able to take the square root of that function. So we're going to look at this and we're going to see how do we identify what the domain for such a function is. So let's go to the last page on our notes. So not all functions have a domain that includes every real number, like I mentioned earlier. Excluded from the function's domain are any real numbers that result in dividing by 0 and any real number that results in an even root of a negative value, like I mentioned again before. So if I have a rational function and I find a value of x that makes the denominator equal to 0, aka I'm dividing by 0, then that number is excluded from the domain. And like I mentioned earlier, this occurs again with rational functions, 1 over x, and your square root function of even roots, like the square root function. So let's look at the example and let's see how we're going to determine how to find the domain of these two functions. We'll begin first with the rational function. Again, the reciprocal function. So here I have a rational function, a reciprocal function that has been transformed. Now, to find the domain for this function, again, the key idea is that I'm not allowed to divide by 0. So I cannot have this denominator here ever equal to 0. So the first thing we're going to do is find what makes the denominator equal to 0. So we're going to set our denominator of 2 minus x. Let me just change the thickness of my pen. 2 minus x, and set it equal to 0. So we're going to solve this equation just simply using some algebra here. We're going to move the 2 to the other side. So we're going to subtract 2 to both sides. Negative 1x equals negative 2. We're going to divide both sides by negative 1. And x equals to positive 2. So if x is equal to positive 2, and I plug in positive 2, I end up with an error because the top is going to be 2 plus 1, which is 3. But more importantly, the bottom, and here's the interesting part, the bottom when I plug in 2 here is going to result in 2 here is going to result in 2 minus 2, which is equal to 0. And here again is the problem. 3 cannot be divided by 0. This again is undefined. So, and this again is only going to occur when I plug in the number 2. If I plug in any other number, let's plug in the number negative 2, I'm going to end up with negative 1 on the top and positive 4 on the bottom. So my answer is negative 1 over 4. I get an actual value out. But when I plug in 2, I get a value that is undefined. So my output value doesn't exist. And because of this, this number 2 needs to be excluded. So our domain is going to be all real numbers except for the number 2, which using inequalities is simply denoted like this. So x cannot equal to positive 2. Now, if I want to write my answer, my domain in interval notation to express the concept that x cannot equal to negative 2, in other words, all real numbers except that value, I'm going to break my real number interval from negative infinity to positive infinity at 2. So I say that x, let me write it as a different form of inequality first before I write the interval. I was getting ahead of myself. That x has to be less than 2 or x has to be greater than 2. So let's now write the interval. So there you have it, okay? So these two forms are the same, just written again using inequalities. And this bottom one here is my interval notation. So read the question carefully because on some of your homework for tonight, you'll be required to either write it in this notation, or as an interval. Okay, but this is how we figure out what the domain is. So let's look at another example. Again, the key thing is figuring out what's going to make the denominator equal to 0. So regardless of what the denominator is, simply set that equal to 0 and solve the equation. Here we have another linear equation. So we have 2x minus 1. And we want to figure out where will this equal to 0. So here we would add 1 to both sides. So 2x equals the positive 1. We're going to divide by 2. And x equals 1/2. So this number of 1/2 will make this be undefined. So f of 1/2 will be undefined. So that means that we need to exclude that number. Now I didn't show you why it's undefined, but if I plug it in right here, 1/2 times 2 would end up being 1, and 1 minus 1 is 0. It doesn't matter what the top is, because as soon as I get 0 on the bottom, any number divided by that 0 will be undefined automatically. So I need to exclude this number. So we're going to say that our domain can be all real numbers except for that 1/2. With using the inequalities, the less than and greater than inequality, that would mean that x would have to be less than 1/2 or x would have to be greater than 1/2, which as an interval notation simply breaks up our interval from negative infinity to positive infinity at this value of 1/2. So we're going to say that our interval goes from negative infinity to 1/2, or it's going to go from 1/2 to positive infinity. And remember, our mathematical symbol for the word or is this letter U, okay? This thing that looks like the letter U. Domain is the square root function or any even root function, not just the square root. It could be the fourth roots, the sixth roots, again the eighth root. As long as this index right here is an even number, it's going to have exclusions. And that exclusion is that the output value, when I plug in a number for the value of x, cannot result in a negative number inside this radical. So how do we determine what numbers to exclude? So for this type of example, we simply get our radicand, again the value that is inside the square root, like in this case 7 minus x, and simply set it to be greater than or equal to 0. That's all you have to do. Solving this inequality will exclude any number that will make this value be a negative, which results in not being able to take the square root. So to solve this equation, we're going to subtract 7 from both sides. We end up with negative 1x is greater than or equal to negative 7, and we're going to divide by negative 1. Now recall from Algebra 1, when solving inequalities, anytime we divide or multiply by a negative number, the inequality symbol is going to switch directions. So x will be less than or equal to positive 7. So that is your domain. Solving in this example, it automatically tells you what the inequality notation for your domain is. So here, all your values of x have to be less than or equal to 7. So as an interval, that would mean that 7 would be the maximum value because all your numbers are going to be less than, and they will go from negative infinity to that 7. And since we're going to include that 7, we indicate that with a bracket. Let's do another one. So in this even root function be all the values of x We're going to solve this equation by first subtracting 5 from both sides. So 2x is greater than or equal to negative 5. Divide both sides by 2. And x is greater than or equal to negative 5 divided by 2. And just a couple of things before I write the domain. Notice I did not switch the inequality. Even though we end up with a negative number, that was the result of moving the 5 to the other side, changing it from positive to negative. That does not change the direction of the inequality. Okay, the only way it changes is had I divided by a negative or multiplied by a negative. But I didn't in this example. I was dividing by a positive 2. Okay, so that keeps the inequality the same. So not every time you end up with a negative value does that mean you need to switch the inequality. Be careful again to only switch it if you're dividing by a negative value here. So this is our domain now. Okay, so moving on, solving this inequality, like I mentioned, is going to be our domain. So the values of x have to be greater than or equal to negative 5 over 2. So that means that in interval notation, negative 5 over 2 is the smallest value, and all the other values of x have to be greater. So they have to go to positive infinity. And since we're including negative 5 over 2, we indicate that using a bracket. So now let's look at the last page, example number 5. These are more advanced examples, and I have them in quotation because they're really not that much different. So for this example right here, let's find the domain of the following function. And because it's a rational function, the technique is the same as before. We simply need to identify the values of x that will make the denominator equal to 0. So here's our denominator, and we're going to get x squared minus 6x plus 8 and set it equal to 0. Now, because it's a quadratic trinomial, the technique, however, is different. This is why I call it a little bit more advanced than our linear equations, because the technique requires factorization instead of our usual techniques of doing algebra, letters to the left, number to the right type of situations when solving a linear equation. So in this example, we're going to factor and break it up into our x squared into x and x. The sign, since the middle sign is -6, that means that the first factor is going to subtract from the x, and the larger factor of 8 is going to be subtracted from x, and the smaller factor of x is also going to be subtracted from x, since a negative times a positive is negative. Now let's identify the factors of 8. And there's only two sets, 1 times 8 and 2 times 4. And of those two, the one that gives us a combination of 6, both being negative, is 4 and 2. Negative 4 plus a negative 2 equals -6. So that's why we're using those two numbers. So from there, that gives us our solution that x would have to equal to a positive 4 and to a positive 2. So those are the two values that will make the denominator equal to 0, which means that when I evaluate f of 4, we're going to get some number in the numerator. We get, well, let me plug it in. So if I plug it in right here, 2 times 4, that's equal to 8, and 8 minus 9 equals -1. But -1 would be divided by 0, which again is undefined. And then when I plug in 2, I will end up with -5 in the numerator, but yet again, I end up with 0 in the denominator. Again, because that's the whole purpose of doing this. This is telling us that the bottom equals to 0. So when I plug in the number 2, this entire thing will equal to 0. And -5 divided by 0, yet again, is undefined. So you see, our function cannot be evaluated at these numbers. So these numbers need to be excluded from the domain. So our answer for this particular question, which is what is the domain of this thing, is going to be all real numbers except for those two values. So we'll say that x cannot equal to positive 4, nor can it equal positive 2. So there's your solution. And then finally, for our last example, before we go to example number 2, let me remind you again some definitions from algebra about absolute value inequalities. From your Algebra 2 class, discussing absolute value inequalities, if the absolute value of x, let's say a variable x, is greater than or equal to some value a, then that means that x will be less than or equal to the opposite of this number, which should be a positive, to negative a, or x will be greater than or equal to that value of a, which in interval notation is represented by the concept that our values of x will go from negative infinity to negative a, and from a to positive infinity. Now, if the absolute value of x is less than a constant a, then that means that our solutions, our values of a, are going to be between the opposite of this number, negative a, and the number itself. So for example, if the absolute value of x is less than or equal to 4, let me pick 5 instead, is equal to 5, then that means that x is going to be between -5 and +5, and it will include those endpoints as well. So let's look at an example now that we have gone over that. Let's look at an example of a quote-unquote a little bit more advanced function regarding square roots. So here our objective is to identify the domain of the following function. Well, like the previous examples, we start the same way. We get our radicand and find what will make our radicand positive. So we're going to set that to be greater than or equal to 0. So x squared minus 9 would be greater than or equal to 0. Now to solve this one, pretty much the same strategy like a linear equation. We want letters to the left, numbers to the right. So we're going to move the 9 to the other side, making it positive 9. So x squared will be greater than or equal to positive 9. Now to get rid of the square, that requires us to take the square root to both sides. and therefore the square root of 9 is equal to 3. And because we're taking the square root, again, with an inequality, this is the quote-unquote advanced part. This becomes the absolute value of x. So to solve this inequality, this non-linear inequality, when we take the square root, we're going to just simply switch this to that. And that happens every single time when doing this algebraically. So to solve this equation right here, again, by definition, since the absolute value of x is going to be greater than or equal to 3, let's go back up here. Then that means this. Then x is going to be less than or equal to the opposite of this number, or x will be greater than or equal to that number itself. So that's going to be our inequality for what values are allowed to be used for x. The absolute value of x is less than or equal to negative 3, or x would be greater than or equal to positive 3. And that's going to be your domain. So those are the x values, again, that are going to exist. So nothing between negative 3 and positive 3 is going to exist. And in interval notation, that will look like this. As a result. So let's look at the graph of this function right here, the square root of x squared minus 9, and look how it compares to the domain. How cool is this? Look at this. Okay, if we look at this, notice that no values of this function. Here's our function right here in red, right? And there are some values that we see. Notice that my x values are going to be less than negative 3, negative 4.7, negative 6.3, and as I move along, they get more and more negative. And then when I get to this point right here is at negative 3. And look, between negative 3 and positive 3, the graph doesn't exist at all. That's exactly what we're trying to determine here. The domain of this thing is telling us again that what we calculated here and what we determined here algebraically is represented again in this graph, that our function doesn't exist between negative 3 and positive 3. All the function we see again as we draw arrows, as we move again arrows to the left and to the right, it's only going to exist to the left of the x value of negative 3, and it's going to only exist to the right of the x value of positive 3. So that's the domain for this function here. How cool is that? It matches perfectly to what we determined in the function itself. So now let's look at the next example. Okay, so for this example, same situation. The objective is to find the domain of this function. So what x are we allowed to plug in that will give us only positive numbers for the radicand? So as usual, we're going to get our radicand of negative x squared plus 9 and set it to be greater than or equal to 0. Okay, that guarantees me that when I solve this, I only solve for values that are positive. Just like before, we're going to move our 9 to the other side. So letters to the left, numbers to the right. And that moves the 9 to the other side. And negative 1x squared will be greater than or equal to 0 minus 9 is negative 9. Here, we do have to divide by a negative 1 since we want the value of x, a positive value. And we end up with x squared. But this time, because we divided by negative, that's going to switch the inequality. So it's going to become less than or equal to positive 9. Now, this still going to guarantee us, again, that anytime I plug in a number, we get a positive value, even though we switch the inequality. Now, the technique from right here, like the last time, is to take the square root. And just like last time, taking the square root is going to result in taking the absolute value of x because of the inequality. If it didn't have an inequality and it was an equal sign, then we won't have to worry about that. This doesn't happen in those type of situations. And now the square root of 9 is 3. So now, this time again, our inequality has switched. The absolute value of x is less than or equal to 3. So if I go back up here just to remind us, then that means that since the absolute value of x is less than or equal to a, then that means that the x's are going to be between the opposite of this number and that number itself. So this implies that our domain here will be all the values between negative 3 and positive 3. So that's our domain. In interval notation, that simply looks like this. Okay, oh, brackets. Okay, brackets. Oh, which I made a mistake. I'm looking at the top answer right now. go back, this should right here should be a brackets, not parentheses because of the equal sign. So it should be a brackets. So let's fix those two errors. And there you have it. So that is going to be the domain for this function there. So the only new part that I'm introducing in these two ones here and these last two examples with square roots is what happens when we take the square root with an inequality. Well, to get again the proper solution, you identify this as the absolute value of your inequality, which will result in a situation like this if it's less than, or a situation like this if it's greater than. So there's your values. Okay, let's look at the graph of this and let's compare it again to our domain.